Hello, everyone. Welcome to the fourth webinar organized as part of the project From Raw Collection to Digital Collection, or simply RCtoDC, co-funded by the European Union. The aim of the project is to enrich the common European data space for cultural heritage using advanced 3D and XR technologies. Before we get started, I'd like to go over a few housekeeping items to ensure everything runs smoothly. Please make sure your microphones are muted during the presentation and to avoid background noise. If you have any questions, feel free to ask them in the chat and we'll address them either during the presentation or at the end, depending on the timing. For any technical issues, please reach out via the chat and we'll do our best to assist you. Also, we would like to remind you that the webinar is being recorded and the recording will be available on our website. Thank you for being here, and let's start. The topic of today's webinar is data processing, editing, and management. But before we get started with the main content, we'd like to briefly go over something that will help you get the most out of this session. Throughout the webinar, we'll be using terms that are specific to the field of 3D model data processing. To ensure everyone's on the same page, we've prepared a glossary of key terms and definitions commonly used in this context. So you'll see a QR code on your screen right now. Feel free to scan it. It will take you directly to our website, where you can view or download the glossary at your convenience. Also, please note that this glossary is subject to updates and revisions. As technologies related to 3D model processing, editing, and management continue to evolve, new terms may be added and existing definitions adjusted to reflect current practices and advancements in the field. Okay, now let's get started. So as I already mentioned, today we'll walk through a full post-processing workflow using Artex Studio Professional. So if you ever captured great 3D scan data and then wondered, now what? This session is for you. So we'll go from raw scans to a clean, textured, and exported 3D model covering captured data pre-selection, data processing, editing, saving and exporting, and finally publishing. As we go through the process, we'll show you all the phases using the example of a wooden statue of St. John the Baptist that we scanned at the National Gallery of Slovenia as part of the RCtoDC project. While the video plays, you're welcome to ask questions in the chat. My colleagues and I will be monitoring it throughout the session, and we'll do our best to answer your questions in real time. Okay, now I will share the video that we prepared for this. Just a second, please. Okay, here we go. So first we open the Artex Studio 19 Professional and connect the Artex Leo scanner to the computer. And we do it by choosing the option Connect to Leo. If everything is correct, if the cable is properly connected and functional, and everything else is correctly set up, we will see which scanner is connected and ready. And then we will click Connect. In this case, we will process data of St. John the Baptist from the National Gallery of Slovenia. So we found it. We will transfer it in one of two possible ways. So we have two options: import raw data and launch scan reconstruction. We can choose both or just one. and we'll choose the option to import only the raw data. That way, we can store that raw data file separately in a folder where we'll keep only the raw data, in case one day we want to start again from scratch and process it in a completely different way than we are doing right now. So we are doing the transfer using import raw data. We pressed import, and now we are waiting for the data to transfer from Artec Leo to the computer. During this transfer, the data is also converted. Since this is a relatively small model, a relatively small sculpture, the transfer and conversion will take only a couple of minutes. So it's a very fast process. The data is converted from a file suitable for scanning into a file suitable for processing. The converted data will then be ready for editing in Artec Studio, which wouldn't be the case if we transferred it directly. So here you can see the rough model. Once the data is transferred from the Artec Leo scanner into Artec Studio, we can first save the file according to whatever Office standard is used, and we will save the file as raw data. So by default, the project is named Project 1, and we can rename it however we want. So we will name it Sveti Ivan Krstitelj, or Saint John the Baptist. And I'm adding Leo here because we may have scans from different scanners as inputs, so it's useful to know which scanner was used. When we begin working, we set aside the raw data file so that we don't edit it, and instead we use a working copy. Again, we can name that according to whatever standard we use. So let's go to save project as, and for example, I'm adding here Sveti Ivan Krstitelj Leo. I'm adding RAD, or in English, work. The raw data is stored separately. It will be good to back it up immediately, either to an external drive or to some other backup. The transfer data is what we will actually use for work. And at this point, we have only SD and HD files on the computer. I prefer to separate raw files into one group and SD files into another group, naming each group accordingly. So then one group has SD data and the other group has raw data. So let's just rename that. And you can see that the raw data can be recognized by its icon, so it's easy to distinguish. Now, the most important part is that we don't want to process the data in regular SD quality, which is good, but not excellent. We want the highest possible quality. And to achieve this, we mark only raw scans, then go to Tools, choose HD Scan Reconstruction, and we choose whether we want all frames in HD, or every second, fourth, or eighth frame. And we can also select the frame quality, normal, high, ultra, or extreme. We choose extreme and we click run. Since you're working on a regular laptop, it might take a bit longer compared to a workstation, but still it runs relatively fast. For a model like this, it takes under a minute for the laptop to process an HD reconstruction of a small statue. So now we are waiting for the HD scan reconstruction to take place. Okay, done. And now we have everything nicely separated. SD scans, raw scans, and HD scans. And to make it even neater, we can rename the whole file, Sveti Ivan Krstitelj, and organize everything. This organization is important because during processing, there will be many different versions, and it's easy to get lost in the variations. Those scans, processed models, point clouds, and so on. If files are neatly named or separated and classified, chaos quickly develops. And we will be working exclusively with the HD frames. The raw frames were only needed to decide which HD quality level to use. And usually the next step is to delete unnecessary parts of the scan. In this case, the surroundings don't help much in reconstruction. So we first remove unnecessary data, such as auxiliary elements used during scanning. And here you can see that we use a bucket to elevate the statue from the ground to make it easier to scan. Yeah. Then we go to editor. Okay, let me just position it a bit. Okay, so we go to editor and click eraser. Here I'll reduce the selection size and we can choose different erasing methods. And in this case, just a second. In this case, lasso selection is enough. So we position the model as you like. And then we proceed to erase the base or surface, which is not needed. Some unnecessary data will remain, so we can use inverse selection to delete it. Even though noise around the model is later removed automatically by processing algorithms, it's better to erase it early. This reduces the chance of stray objects remaining in the scan. So for example, if someone walked past during scanning and the scanner accidentally captured a person, a hand, or some closed objects. So after cleaning, we reload the model without the base. So some elements may still remain, like a bit of the base, but we can remove those later. Waiting for it to load. Okay, and then we go to Tools, Registration, and we will choose Global Registration and set it to use features, geometry, and texture. We keep the default settings, so keyframe ratio 0.3, and search within features within 15 millimeters. These are the optimal default settings for HD scans from Artec Leo. In specific cases, we might adjust them, but for this statue, since we were able to assure that the sculpture was put in an upright position on a base and with ample room to move freely around it, the Artec's default settings work perfectly in our case. And we also keep the smart subsampling enabled and run the algorithm. If we have very thin objects like tiles, we would enable thin objects. In this case, it might have been useful to enable focus on geometry, since the statue is smooth and white with few texture features. However, there are enough texture features that I didn't enable it. For fine frame alignment, global registration benefits from using as many features as possible. So every small scratch or texture detail helps frame-to-frame alignment. So here I chose both geometry. I chose both geometry and texture. The focus on geometry option will only speed things up in cases where a model has no texture features at all, which is rare. After global registration, we can check the quality by looking at the error column, which shows how well the frames aligned with each other. So about 0.2 millimeters here. And now that the global registration is done, we can clean up the pedestal a bit more. We could have done this earlier, but it actually helped in aligning the lower parts of the statue. So we will go to editor. And eraser. And we can do this with the base selection option and the cutoff plane selection. And in this case, I'll choose base selection. The base selection option automatically finds a surface, and that way the entire bottom part can easily be deleted. On the other hand, if you are precise and have a steady hand, it's even better to use the lasso selection option when the scan is neatly positioned. And the lasso option is also faster. So we're cleaning those bits. So the bottom part is neatly deleted without issue. So sometimes it's good to use automation, and sometimes it's better to do things manually. After deleting that, we can check what's wrong with this one frame. In one group, we have a 0.2 error and an exclamation point. Those are usually bits of data that weren't captured properly, some noise or something very small. So we can check what's wrong with this. So we go to error option, and we have only one frame that's slipped. So we can zoom in and see what it is. And it's just some meaningless small fragment that we can delete right away if it bothers us, or we can simply exclude it later from the reconstruction. I'll delete it here since it's really just a tiny scrap that serves no purpose. And it looks nicer this way. But like I said, we could have left it and just ignored it during reconstruction. So all the frames recorded and aligned in this HD group are aligned to each other with a maximum error of 0.2 millimeters. That's very good. And now that the global registration is complete, the next step would be to clean the noise. As we can see, there are some dots, some elements that are not part of the actual object. These must be removed before reconstruction, that is before making the mesh model out of triangles. And we are going to mark these frames. And And then let's go to Tools, choose Outlier Removal. And we leave the 3D noise level at 3 and 3D resolution at 0.5. And then start the algorithm. These, as mentioned earlier, are the default settings for Artec Leo HD. And since this is a textbook example, we'll keep the default settings and proceed with cleaning. Now, in some cases, it's not good to clean with default settings. Sometimes we may have areas that are hard to scan, like holes, perforations, or transparent surfaces. Things the scanner struggles to capture, like glasses, deep cavities, and so on. In such situations, when we run this algorithm that cleans noise, it may also remove good data that was just difficult to capture. That's why we can use this algorithm with default settings only for the parts that are easy to scan. For certain areas, we can copy the point cloud, clean only those parts manually or with custom settings, and later merge them back into the base scan. That way, the whole scan is cleaned properly, but tricky parts like under the arms, behind the legs, or deep folds are preserved. Because otherwise the software would delete real data we need. And we don't want the program to remove useful details. So we clean partly with default settings and partly key pieces where we intentionally left some noise. Because we know that noise is actually useful raw data from which we can later reconstruct the final model. If we deleted it, we'd end up with holes and undefined spaces that we have to then invent or fill in. And we actually had that data, but the outlier removal algorithm deleted it. So we must be careful with outlier removal. Sometimes it's not best to let it do everything automatically. In this case, we don't have tricky areas. The statue was relatively easy to scan, so we'll clean everything using the default settings. And if it happens later that some data is missing in the construction, but we know we had it in the base file, in the raw point cloud, we can always go back and extract just those positions we needed. So it's always good to be able to return to the original raw data, because things we lose deliberately or accidentally during processing can always be restored. Okay, now we are waiting for it to finish. And now this algorithm takes a bit longer to run compared to others which finish faster. So we will just skip a bit ahead. Okay, the process is finished, and as we can see, the noise is cleaned and all the lines are now much finer. Here we can see those elements that we mentioned earlier, those which might have been captured but were cleaned out by the algorithm. So those bits over here. And here. The next step would be creating a 3D model in the form of a polygon mesh. In Artec Studio, this is called Fusion. And since we have good input data aligned to within 0.2 millimeters, 0.2 millimeters, we can now set the maximum mesh resolution to 0.4, and this number must always be larger than the error. During reconstruction, we'll close holes by radius with a maximum radius of 25 millimeters. That means if we scan an object with openings of 2.5 millimeter radius, this is the threshold the software will fill in. We'll turn off filter frames by error, since in this case we don't have any remaining errors. At the start, we had that one small fragment with an exclamation point, if you remember. Here it was. And now it's gone. And we'll do the reconstruction at ultra sensitivity, which is the highest setting. And we'll also set maximum resolution, and then we will start the algorithm to create a 3D mesh. RTX Studio works in triangles. Most reconstruction software uses polygons, and RTX chose triangles as the base. Since we use HD frames at extreme quality and we selected ultra sensitivity, the smart reconstruction is heavily loaded. So it will take about a minute to reconstruct the 3D model, which, all things considered, isn't long. If we had fewer input frames, the 3D model would be created even faster. Okay, here we go. The model is made. And now we will check where data needs patching. That is where the holes are. So let's look for it. For example, the pedestal the model was standing on, that wasn't reconstructed. So there's a hole there, as you can see. So we will choose the option Fix Holes. And we have several options here. We can close holes flat or close them smoothly. Since this statue is made of curves, if there's a hole, it's better to close it with smooth, because that blends the surface naturally. And if we were closing a flat surface, like a tabletop, then flat would be better. And there's also an option to smooth edges and to build bridges, which means connecting one side to another with a strip. That wouldn't close the hole, it would just span across it. And we don't need that right now. What we want is to close holes. And here you can see that the holes are listed by size. And here's the largest one. So we can close it with either flat or smooth filling mode. And I'll choose to close all holes now, just to demonstrate how it closes the one behind the leg and the one below it as well. Behind the leg, you can see. With smooth, we can also see that behind the belt, it blended nicely. Otherwise, it would have been flat, and we'd have to manually correct it. And then behind the knee, the hole was also closed smoothly. However, where the holes were closed, there's sometimes a bit of bumpiness that can later be selectively smoothed. For example, the bottom part was closed like a cushion, and that's something we can easily cut off later. Now we click apply. And then we'll go to editor, where we can use the smoothing brush to clean up areas that were automatically filled, if needed, of course. Usually the automatic smoothing does a good job, and no extra work is required. But anyway, here's the finished model. And sometimes situations arise where we need to transform or do the rough positioning of the object in space. But in our case, during scanning, the model was nicely oriented already. So top view, bottom view, everything aligned correctly in the coordinate system. And the feature brush is another useful option when there are unnatural bumps or oddities on the surface. But here, everything is clean, well scanned, and doesn't require much correction. Now, the only thing left is to remove the base. And we could delete it directly in the eraser using gloss or base selection. But instead, we'll use a cutting plane to slice the model neatly. There are several ways to do this. We'll ask the software to place a plane using some preset positions, and then we'll adjust it. Okay, let's say we are satisfied with this position. We go to edit and we choose split object. Then we choose the object that we want to split and the plane. And we can choose whether to keep the original hole after cutting, but we don't need that here. And now we have two models, the top and the bottom. And the bottom cushion or base isn't needed, so we can delete that. And now the pedestal is neatly cut off. We can keep that cutting plane if needed or delete everything. And then we can rename the model appropriately. Okay, let's rename it. So we now have a triangle mesh model, as you can see. And if we switch to wireframe view, we can see the dense triangle mesh making up the model. If we want to correct anything on the mesh, it's best to do it now. This means going over the entire model and checking whether any holes were closed improperly or if there are inconsistencies. So for example, if fingers were fused together or areas smoothed over that shouldn't have been. So let's check thoroughly for all of that. Maybe the software closed the head area, smoothing it, while in reality there's an opening on the top of his head. So that's sort of thing we have to keep in mind. Also, we can see that the algorithm filled in the space between the chest and the band, when in reality there should be a gap there. And that's why it's important to thoroughly check the model, look at the reference photos, compare and confirm. And corrections should be done now because later, if we do them on a textured model or at a later date, it becomes harder to notice or fix errors. And it's also a good idea to keep version control. We can label them A, B, C, D, so we know what changed in each version. And it's also advisable to write down what the change was. So let's do that. Renaming it. Now here we have Sveti Ivan Krstitelj in HD. And I'll add original variant, so I know it's the clean, untouched base file. Every new edit, whether we cut, add, or merge with other data sources like photogrammetry or another scanner, that should be saved with a new name that describes what was done. And in this case, I'll duplicate this model and continue working on the copy. And I will simplify and optimize it. So we go to Tools, Mesh Optimization. And here I will choose the options Remove Small Objects and Heal Bad Polygons in order to clean floating objects or badly reconstructed polygons. And I will leave max linear error to its default setting of 0.2 and run the algorithm. Now this new file is only 3 megabytes and has over 166,000 polygons. Compared that to the original, which is 101 megabytes. Visually, when switching to solid mode instead of wireframe, the difference is barely noticeable. So you must choose a simplification level wisely. The goal is to keep the geometry accurate, avoid creating a caricature, but still preserve the form. And for this model, the 0.2 was the right factor. Every model is different, so it's important to experiment and to find the optimal simplification level. Okay, so the next step is texturing. We can apply texture to either the original model or to the simplified one, but applying it to the simplified model is much faster, and visually the difference is minimal. So we select the model, choose the scans, and here we will use the HD scans from the Artec Leo scanner, and then we select the output texture size. In this case, we'll reduce the texture resolution a bit to speed things up. And we'll also leave glare reduction off. That way, all natural reflection and highlights from the statue remain in the final texture. And we want to retain as much of the real appearance as possible. The software will also fill in missing texture in places where no texture was captured, like under the cloak or behind the statue. Those parts weren't reconstructed, so no texture was recorded there. The software will use inference, essentially inventing texture that's visually similar to the surrounding areas. It won't be real photographs of that area, but it looks better than leaving those regions black or undefined. And since we simplified the model earlier, the software made a mistake, so it deleted part of the surface. So we'll fix it by deleting what's left and filling the hole. Okay. So we'll go to Fix Holes and choose the flat filling mode. And then we return to texturing. We choose texture, select the scans again. And click Apply. Now, because we are working with fewer polygons, the algorithm runs very fast. So let's just wait for it. After texture generation, we can adjust the appearance. So we can modify contrast, gamma correction, and other properties. And if we are not happy with the result, we can reset everything and start over. So let's just see those features. Okay, see gamma corrections. It's a good idea to keep the original version and to make a copy to experiment on. Okay, now I'll rename this version of the statue. It's not original anymore. It's something like Saint John the Baptist or Stephen Christopher. HD, simplified using factor 0.2 and adding 4K texture. That way, the name clearly communicates what's been done to the file. And when exporting, say, to Sketchfab or for use in other software, it's important that the object's name reflect its properties. In the properties viewport, we can check how large the file is, see the polygon count, confirm it's textured, and also check the wireframe check the wireframe to verify certification. And we won't apply texture to the original object since we already textured the simplified version. In this simplified version, since we didn't enable anti-glare, reflections and glare remain in the model, as you can see. That's okay for now, but if needed, we could run a pass to reduce glare before texturing. And now that the model is finished, we can export it for use in other software. So we go to Export, select only the object that we want to export, and we export it as a mesh into the desired format. And there are several options here, PLY, STL, OBJ, others. In this case, we'll export the model as OBJ for geometry and PNG for texture. And we'll name it exactly as it appears in RTX Studio. Just a second. We copy it. So export meshes and name Saint John the Baptist simplified 0.2 plus 4K texture. Okay, then we choose a destination folder, typically the same RTX Studio project folder. Okay, select it. And for the model export format, we choose OBJ. For texture export format, we choose PNG, and we export it. Okay, now let me just go back to the presentation. Just a second, please. Okay. So in this video, you saw the processing of the model in RTX Studio Professional, and that same model is being shown here on this slide. So here we are looking at a comparative analysis of the textures of 5 3D models of Saint John the Baptist that were created using a wide range of equipment. So from high-end scanners to a smartphone. And the model scan with the RTX Space Spider was processed using the anti-glare function, resulting in a texture free of glare or reflections. And in contrast, the RTX Clio model was generated using onboard photos without anti-glare, which caused visible glare on the statue due to the built-in flash. And then models created using the Canon EOS R5 Mark II and the iPhone 16 Pro Max, they show no visible glare, as the textures were captured without using the flash. However, shadows are present in deeper or less illuminated parts of the model. And And this comparison demonstrates that good quality results can also be achieved using consumer-grade equipment, so depending on your specific needs. But however, if we were to zoom in closely, differences in geometry would become more noticeable. Okay, and now that we completed the workflow, so from scanning to processing, and then editing and exporting, the final step is publishing. To make our 3D models accessible and shareable, we here at the RCtoDC HQ, we use Sketchfab, a widely used platform for displaying interactive 3D content online. So you can customize lighting, background, and materials, and even add annotations to guide viewers to key features of the model. Sketchfab also supports augmented reality, allowing users to view models in real-world spaces using mobile devices. And that's great for education, exhibitions, and remote audiences. Sketchfab offers several account tiers depending on your needs. So we have the basic plan, which is free and allows up to 10 uploads per month with a maximum file size of 100 megabytes per model. Then there is the Pro plan, which supports up to 50 uploads per month and 200 megabytes per model. And lastly, the premium plan offers 200 uploads per month and supports models up to 500 megabytes each. So this gives you flexibility depending on how frequently you publish and the size of your 3D files. Of course, Sketchfab isn't the only option. So there are other platforms available. Some of them are open source, like Model Viewer, which is a web viewer. Also, Microsoft has a 3D viewer that is free and accepts all the popular file formats like OBJ, STL, PLY, GITF, GLB. Then there's also MeshLab, which is free software for editing meshes. You can also use it as a viewer, and it's available to download and install for free on your PC. Another option is Blender, which is open source software for 3D modeling, among many other capabilities. But it also allows you to edit meshes and structures and use it as a viewer. And then there are platforms with paid subscriptions, like Nira, which offer different levels of functionality and hosting options. And Nira is mostly for large-scale 3D models, review and collaboration, especially for architects and engineers dealing with massive assets. And we've also prepared a short video explaining Sketchfab's features. So let me share the screen or the video. Just a second, please. Okay. So Sketchfab. Okay, here we go.
Today, I'll be walking you through how to use the Sketchfab platform to view and interact with 3D models. Currently, we are on the RCtoDC's profile where you can see all the uploaded models. Let's begin by opening one of them. I'll open the altar of the Holy Cross from the Church of St. Cross in Križevci, Croatia. Once you click on the model, it might take a few seconds to load, but don't worry, that's completely normal. Now, once the model is loaded, here's how you can explore it. If you left-click and drag your mouse, you can rotate the model and view it from all sides. If you right-click and drag, you will move the model up, down, or side to side. Using the scroll wheel, you can zoom in and you can zoom out. And if you double-click on a specific part of the model, Sketchfab will zoom in and focus right on that area. This makes it easier to examine fine details. Next, let's take a look at the settings and tools available. These are located in the bottom right corner of the model viewer. The first icon you'll see is the Help button. When you click it, you'll get navigation instructions in English. Very useful if you ever forget how the controls work. Then there's the settings menu. This lets you adjust navigation and textures. So, for example, we can switch to first-person view, and you can use the keyboard to move around. Another powerful tool is the Model Inspector. This feature gives you a deeper look into the structure of the model. You can examine material and geometry. For example, you can switch to wireframe view and see the polygon mesh. You can even explore UV maps. It's perfect if you want to understand how the model was built. Sketchfab also offers different viewing modes. If you want to see the model in augmented reality, you can click on the View in AR button. This allows you to place the 3D model into your real-world environment using your phone or tablet's camera. So, for example, you could see how a sculpture might look in your room. If you have a virtual reality headset, you can enter VR mode by clicking the View in VR button. This will let you step inside the model and explore it in a fully immersive way. Just make sure your browser and device support VR viewing. There's also theater mode, which gives you a larger view of the model without hiding the rest of the web page. And if you want to go completely distraction-free, click on full screen mode to fill your entire screen with the model. Just click again to exit when you're done. Now let me explain how to use augmented reality with your phone or tablet. Here is how it works. First, click the AR button on the Sketchfab page. A QR code will appear on your screen. Open the camera on your phone or tablet and point it at the QR code. A message will pop up on your device asking if you want to open a link in your browser. Tap that message. Once the page opens, tap the View in AR button. The first time you do this, your device may ask for permission to use the camera. Just make sure to allow it. Then point your device's camera toward the floor or any flat surface. Slowly move your device around until the model appears on your screen, placed directly into your surroundings. And that's it. You're now ready to view, explore, and interact with 3D models using Sketchfab. I hope you found this helpful.
Okay, let me now just stop the video. Okay, and let's go back to the presentation. Okay. And that's it for today. For today's webinar. Thank you so much for joining us. I don't see any questions in the chat. I don't know if maybe somebody has some questions. Feel free to send them also in the chat. We'll leave it open for a while, or you can also send us. You can also send us an email. I'll wait if maybe somebody asks something. But we appreciate your participation. We hope that today's session has provided valuable insights to support your continued success in 3D scanning and digital asset creation. And before we wrap up, we would like to also invite you to follow us on our website and social media accounts for more information about the project, and also to stay tuned to hear about our future webinars. Also to ask any questions. If you don't want to ask now, you can ask them via the chat, via the socials. And I would also like to, we would love to hear your thoughts. So if you could please take a minute to fill out our feedback form. Your input helps us make future sessions even better. So thanks again for being with us today, and we hope you found it informative. Thanks.